Discussing the topic of pitting corrosion. In the previous class, we discussed the fundamental or the basic mechanism of pitting corrosion. We saw that the pitting corrosion essentially occurs in what metals? Metals exhibiting the passivation. So that is an important criteria. The second criteria is that the pitting corrosion occurs in selective environments actually. You must have a species that should induce pitting corrosion. This is the second important factors. The coming to mechanism, we said that the pitting corrosion mechanism can be considered as pit initiation, metastable pitting, and then a stable pit growth. The understanding of the pitting initiation is not still well understood process. We saw that the factors that cause the pit initiation are, you say, the applied potentials which will break the passive film. The breakage of the passive film is assisted by the environment like chlorides and all kind of things. And but then when you start initiating that, when the film breaks down occurs, it is not guaranteed that wherever the film has broken will lead to ultimate pitting. There will be always damage of the film, the repassivation of the film, they occur in a dynamic manner actually, that we call it as a metastable pitting. Of course, there is a damage to the metal. If you observe microscopically, there are submicroscopic or microscopic level pits are occurring, but these pits not necessarily stabilize. We looked at the stabilization criteria. The stabilization criteria for the pitting is what? Is that the pit has to have its own chemical environment. That chemical environment must be acidic, it must have also rich in the damage causing species such as the chlorides. So, whether the pit will be stable or not depend upon how good you may able to stabilize the environment within the pit. Outside the pit, you are going to have a normal chemistry, what is taught with actually. Within the pit, it is an occluded cell. Now, there are dynamic processes, the metal dissolves, it releases cations actually, they go from the pit surface to the pit. From the pit, the metal ions migrate outside the pit, goes outside the mouth of the pit, right. If they stay within the pit, they hydrolyze, giving rise to what is called as H plus ions. That also leads to the migration of the chloride ions because of maintaining the charge neutrality. H plus means more positive. So, the cation hydrolysis, okay, which decides the pH of the environment. So, there are two processes, the dissolution process and the migration process. That is why we said the criteria for pit stability is radius multiplied by the I. That is the criteria that the pit could be stable or not. Now, of course, we can go in deeper in studying the pitting mechanisms and various factors. I think since it is a first course on corrosion, we will not go into depth on the mechanisms. Now, what we are going to look at today, two aspects. One is the pitting characteristics and the factors that control pitting corrosion of the metals. What are the governing factors? The second aspect of that is how do we control the pitting corrosion and how do you evaluate or test a material for pitting corrosion. With that, I think we will be completing the discussion on pitting corrosion of metals. So, let us look at when do you call a pit? You have uneven corrosion occurring on the surface, right. In fact, most uniform corrosion that you see or they are uneven. You can visually see there are rough surfaces. You see industries when you go, the steel surfaces are covered with the oxides, ferric oxide, okay. Remove it, you see surfaces are undulations. Now people mistake it as pitting corrosion. Now you should be able to define when you call that surface undulation as the pitting. The one of the criteria is called as a pitting factor. The pitting factor is given by, okay, and before I do this, I draw this diagram of corrosion leads to pitting. This is a pit you see here, right, and there is also uniform corrosion occurring on the metal. This is the D average corrosion. Uniform corrosion you may call it, and this is the depth over which the pit has occurred, D. This is the pit depth. Now the pitting factor is given as D upon T is a pitting factor. So it should be greater than 1. Then you call a pitting. If it is not greater than 1, you do not call it as a pitting. The other way of defining the pitting is it should be depth of a pit upon the radius. When I say radius, it is a gross radius. You are not going to have a perfect circle, right? Okay. Perfect hemispherical this thing. Okay. You should be, I think some people define it, it should be greater than 1, some people call it as 2. So you have a very shallow kind of thing, then it is not pit. Now this makes sense, right? If the pit radius is very large and the depth of the pit is very small, what happens? Can you connect it to the mechanism? It is not crevice corrosion. The migration becomes much easier, right? It is no more diffusion control and you can subject it to convection, right? If it is so shallow, the metal will just get out of the pit. It will not sustain a pit chemistry, right? So this is to sustain a pit chemistry. So that the pit becomes very stable. The people also have been following the pitting kinetics of various metals, and some people have come to this kind of relationship, the pit depth is related to K T to the cube root, that this thing, okay, and D means the depth of the pit, right, and K depends upon what? K depends upon the environment. Please understand, this is related to growth rate, it is not related to pit initiation. The pit initiation may take weeks, it may take a month, it may take a year, whatever, but this only talks about the pit growth, it does not talk about pit initiation. What is T here? The T corresponds to the time of exposure. It is necessary to understand that pit is not only one shape, you can have a complex shapes, you can have a different morphology of the pits, okay. So, it is necessary to recognize that actually. So, we see that there can be different morphologies of the pit, and if you want to know more details, you can look at this standard ASTM G46. It talks about identification, and examination of the pits. It talks about various pit morphologies. I just reproduce some of them here schematically, right, and let us say you will have is called narrow, deep pit. You can have elliptical pit. You can also have wide, shallow pit. You can have pits which are subsurface. You see here, it just undercuts, just undercuts, just subsurface pits. It grows like a internally it grows like that, and there are some. Let me see if I have some photos. Yeah, there are some examples of how it goes. I suppose you will be able to see this. This is a pit here, and pit has grown sideways, and from the bottom start corroding up, and so you see the pits here, very fine pits. So you see a small corrosion, and there is a lateral corrosion taking place, right, and from the bottom it just starts corroding, and ultimately leading to this kind of morphologies. Okay, you see this kind of things could happen in the systems. You also see a similar things here. These are all corroded and then lifted. see this is about to lift here, about to lift, just about to lift here. So, these are the portions, you know, I hope you are able to see this here. Look at this, okay, and it's corroded from the bottom and moves up and then it just goes away. So, you can have a very complicated pit morphologies, it can happen, okay. You can also have sometimes very strange undercutting, something like that, you know. Sometimes, you know, sometimes it follows the microstructures. If suppose you have some jazz follows all kind of things, okay, microstructural dependent. Okay. It just takes the shape of the microstructures. I think I have shown this in the beginning of the earlier class. Let me just see if I can fish up that slide. Yeah, you can see here, right? These pits are all taking the morphology of, this is a composite, silicon carbide composite, and so the shape of the composites are taken here. So, it can take all kind of complex shapes. So, you can have a nice hemispherical pits and you can have complex shaped pits depending upon the alloy, because alloy is not homogeneous all the time. It can be chemically, it could be heterogeneous, and so there can be you know, uneven type of corrosion morphologies for pits. Now, let us look at the factors that control the pitting corrosion, because if you understand the factors controlling pitting corrosion, then you can able to, you know, prevent pitting corrosion. Broadly, I would like to say that there are two kind of factors, one related to the environment, and the second one related more to the metallurgy. Let us look at these factors briefly, and let us look at these factors briefly. Let us look at the environment. We have seen the condition is you should passivate, right. Should have aggressive ions. Mostly the halide ions are considered to be aggressive. What are these halide ions? Anybody remember? What are they? They are fluorides, bromides, and iodides. When it comes to stainless steels, the most aggressive is chloride, next is bromide, and the fluoride and iodide, they are not really that aggressive. Okay. Now, you know, broad, I mean, you can say kind of broad, I would say, I think, so I mean, broadly speaking, I would say, okay, not really actually, one can verify all these parameters. Fluoride, see, if you have a passive film, if the passive film has to get damaged by these ions, the ions have to migrate in the passive films, right. they have to migrate and then form a complex, all this possible. The migration depends upon what? The radius of the ions. If the radius of the ions is too big, then migration becomes very difficult. So if you take it that way, fluoride is ionic radius should be smallest as compared to chloride and bromide and iodide, but even then the fluoride does not cause severe pitting as compared to chloride for two reasons. One, the fluoride forms complex and so promote more uniform dissolution. The second reason is the fluoride forms strong hydrated layers. See, these ions in water are not very free, they are hydrated. The water molecules, I mean these ions are enveloped by the water molecules. Even if you take H plus ion, they are not free. H plus ions are covered with what? Covered with water molecules. Why? Water is a polar molecule, it has got a positive charge and negative charge, and so they get enveloped. So when you have a fluoride, it is getting hydrated, it's very strongly hydrated, then you do not allow the water to come out and free the fluoride ions, because to remove the water molecule from the fluoride ions are more difficult because the charge density is more on fluoride as compared to the chloride. So the two reasons make the fluorides less aggressive towards pitting as compared to the chlorides. And iodide is the largest radius. So it does not pit. Does not cause pitting rather actually, okay. Now there is a kind of empirical or thumb rule that the pitting tendency is related logarithmically related to the concentration of the aggressive ions. Something like you can say E pit is equal to E minus A log chloride, something you can say that. So the E pit will decrease if you increase the chloride ion concentrations. A, this factor depends upon the nature of the aggressive ions. So higher the concentration of chlorides and more susceptible they are towards pitting. It also depends upon the pH. Okay, lower the pH, more is the pitting. Tendency. It also, what happens now, it's easy for the pit to stabilize an acidic pH, right? You have H plus ions in the solution. You also have one more thing, that is the nature of the cations. Suppose I add cupric ions, I add ferric chloride ions, for example, ferric ions. So, what do you think will happen to pitting? When I add ferric chloride, let us say I have taken stainless steel and immersed in sodium chloride solution, and maybe it has taken 6 months to pit, right, 304. When I add ferric chloride, what do you think will happen? Will the time for pitting will increase or decrease? It won't change at all. Can you remember some time back I gave a very an empirical relationship that E pit is a function of what? Function of chlorides, time, and of course the applied potentials, right. The pitting tendency, I said that is a function of applied potentials, concentration of the species, that time of immersion, right. Now, when I add ferric chloride, what happens? What do you think will happen? Any idea? What is the nature of ferric chloride? Why you have chosen ferric chloride? These oxidizing species, right? The standard potential of ferric and ferrous ions equilibrium is quite positive, right. So, when I add these ions, what happens? What will happen to the corrosion potential of stainless steel in sodium chloride solution? What will happen?
It goes up.
It goes up, right. So, when the potential goes up, so what will happen to tendency of pitting? Increases, right. So, when you add these ferric ions, these are oxidizers, so they promote pitting because they are all oxidizers. On the other hand, suppose I add, let us say sodium chloride or nickel chloride, they are not really going to change the potential of the electrode potential of the corroding metal. They may not have very significant effect on pitting corrosion. So, what about the temperatures? What do you think will happen to pitting corrosion? When the temperature increases, so what will happen to pitting corrosion? Diffusion will become faster, what more can happen actually? That is only one aspect of it. What also happened to the dissolution of the metal ion at the pit? Increase, right? So, it is going to increase. So, when rise the temperature, when the temperature is increased, pitting tendency also increases. In fact, they also make some of the salts, formation and the salts, and then it stabilizes the lower pH and stabilizes the chlorides. So, rise in temperature is always detrimental towards pitting corrosion. Now, some of these ions, say chromates, silicates, molybdates, okay, and even you add even hydroxides, they inhibit pitting corrosion. In fact, for aluminum alloys, to improve the pitting tendency, they give conversion coatings. They give conversion coating with chromates. Okay, the chromates indeed promote resistance against pitting corrosion of aluminum alloys. Let us look at the metallurgy. Here we are not going to look at a host of materials, say titanium undergoes pitting and almost all passive metals will undergo pitting, okay, given the conditions. So we will just confine mostly towards stainless steels, very broadly used actually, okay. So let us look at the metallurgical aspect of it. When I say metallurgy, we say the composition, one aspect, 2 the microstructure, right. You can also talk about the surface nature. It is not really metallurgy that way, surface nature. Now let us take the case of stainless steels and discuss these aspects in details, because stainless steels are very widely used and they are prone to pitting corrosion. What are the constituents of stainless steel? Anybody? Of course, base alloy is iron. You have nickel, you have chromium, you have molybdenum. Sometimes people add nitrogen, they add tungsten, they add copper, and sometimes they can add manganese kind of stuffs, okay. Silicon, for example, they add actually. So let us look at how these alloying elements affect the pitting tendency of the metal. Now the pitting tendency of the metal you could define by some electrochemical parameters, right. What are the parameters? Anybody recollect? What are the parameters that you can use to measure the relative resistance of an alloy to pitting? What are the parameters? What is, yeah, please, what is that?
Pitting potential.
Pitting potentials. And other one is called as repassivation potentials. Okay. Now let us look at this, how various alloying elements affect these two properties. So schematically, this is the forward scan, backward scan, right. From the corrosion potential, you rise the potential, you get, what is this called? This is called as, what do you call this current density? IC, I critical current density. And what is this called? I passive. And what is this one? E pit. And this is called as E repassivation potentials. Now let us look at the elements that can affect this. The elements that move up the E pit are going to improve the pitting resistance of the stainless steels. So what are these elements? These elements are chromium, molybdenum, nitrogen, tungsten, silicon, vanadium and nickel. So these elements, they increase the pitting potentials. So when you increase the pitting potential, that means the initiation tendency of the metal to pit is reduced. What about this? If it goes up, it is good. This is called repassivation potential. If it goes up, these things you have molybdenum, nitrogen, tungsten and chromium. Of course, you want to know about the passive current density, if it wants this to be reduced or not. The passive current density is reduced, these elements chromium, nickel, tungsten and nitrogen to a certain extent. And you want to know about this one, what is this potential called? E primary passive potential, right. What are the factors that affect this? And see, nickel is not good, it increases, and so as copper, it increases. Which one decrease this IC? Now these elements like chromium, nickel, vanadium, moly and nitrogen. So in fact this forms a basis for development of various types of stainless steels, right, which are resistant to corrosion in general, right, fitting corrosion in particular, crevice corrosion in particular, okay, and this forms the basis of that. Of course, you cannot keep adding the way you want, suppose I take a austenitic stainless steel, I want to increase the pitting resistance, I cannot keep adding so much of chromium, right. If you add it, what happens? The austenitic phase will turn into a ferritic phase, okay. So then you need to make a phase balance, so you need to add nickel to it, right. So the wire development is a different story altogether, right, but the corrosion resistance story depends on this diagram, okay, and in order to get different phases you compensate with the relevant alloying elements, okay. So that is a different story of physical metallurgy of stainless steels, we will not be discussing over here. Now if you look at here, there is also an empirical equation, okay, and to correlate alloy chemistry to pitting corrosion, that is using PREN is the term is an index which is given as percentage of chromium plus 3.3% of molybdenum, again 0.5 of tungsten plus 16% of nitrogen. What is PRN? It's called as pitting resistant equivalent number. Okay, and you can say that if PRN increases, pitting resistance increases. So for applications involving large amount of chlorides like seawater applications, the stainless steels with a higher PRN are being developed. Some of them in fact are in use, okay. Now I give some example here. I hope you can able to see this chart here. It is this represents various austenitic grade stainless steels. You can use this kind of things for even ferritic grade also, you can do that. What is given here is the PREN number, starting from let us say 15, right, is going up to let us say 60, okay, and see the stainless steels have been developed from starting from here up to this, right. This is called as the 654 SMO, okay. This got a 6 molybdenum, okay, is higher amount of molybdenum is present here, okay. Now you cannot add a high amount of molybdenum because it becomes a ferritic stabilizer, so people add more amount of nickel to that actually, okay. So this is also you have 254 SMO, this 254 SMO, okay, this and 25 chromium you have actually, okay, and so you find that, and so the various kinds of stainless steels are being developed in order to have higher repeating resistance, which means they do have higher PREN number, but the cost of this also going to go high, right. You have more nickel, more molybdenum, it is really increasing its cost of it. So that is one of the problems of using austenitic grade stainless steels. So what happened was that, okay, there is a variation of this. People use what is called as a duplex grade stainless steels. It's somewhere in between, nickel based alloys, and okay, nickel based alloys also have very high repeating resistance. Now the cost of the duplex stainless steels with high, at high PREN number are lower compared to the cost of austenitic stainless steels at high PREN number. The reason is very simple. The nickel content in duplex stainless steels are all going to be mostly lower compared to nickel content in the austenitic grade stainless steels. So again there is a gradual growth of duplex stainless steels with low PREN number, it going up to 40, 46 and so on. Now look at this duplex stainless steel can be used in seawater application where the chloride content is 3.58%. Similarly, you can also use 254 SMO, okay, sorry 654 SMO, you can use that, and but then this is prohibitively very expensive, this material here compared to the duplex stainless steel here, okay. So what I am trying to say is that the development of stainless steels were based on understanding the chemistry of the alloy towards the pitting corrosion of the metals actually. In all this, the nitrogen plays a very significant role. Let me just see if I can show you some kind of curves here. Let me show this polarization curve, okay, and see it is essentially it's a 904L filler wire, you know what is called a cladding, right? What is a cladding? And you melt and deposit. You can also deposit without melting also actually, right? It's a layer of in this case 904L formed on mild steel here, okay. This is done by welding, by weld cladding. So melt it and apply on the mild steels, and it's 904L, okay. So what happens? See in this case the carbon steel, why people go for cladding? Because you want to go for higher corrosion resistance materials, you want to have a thick one, it's very expensive, right. So you can go for a carbon steel or other steel having lower cost, go for a thicker component, you just deposit a clad layer of let us say 2 or 3 millimeters that takes care of the corrosion, and the basic substrate takes care of the strength characteristics, so it becomes cheaper. Now we have done some work related to 904L, okay. Look at this here, it starts with this is the 904L without adding any nitrogen. When you start adding nitrogen further and further, you see what happens now, the pitting potential increases and even the repassation potential also increases. Now in this case the nitrogen content is 0.245. So when you add to the weld more nitrogen, what happens? The pitting resistance increases significantly. Please see here the weight is it's about 0.258% only, it's not too much. So by adding this nitrogen you can increase pitting resistance from E-pit value from minus 400, it has gone up to 1.2 volt. In fact 1.2 volt means it is not pitting actually. If you look at the Fourier diagram, it will be what? It will be oxygen evolution reaction. Okay. So essentially this does not pit at all by just addition of small amount of nitrogen. So alloy development can be done to improve the pitting performance of stainless steels. Because pitting corrosion also is very widely studied from the mechanistic point of view. What I mean by that? When add molybdenum, when add nitrogen, they are much more effective as compared to chromium actually. So people have studied why molybdenum is very effective. People have studied why nitrogen is very effective, because there is no lost word, right? Still there are multiple theories as to why molybdenum improves pitting resistance, as to why nitrogen improves pitting resistance. I just summarize a few of that and then move on to the next topic. The molybdenum, the role of molybdenum has been first of all they say that molybdenum is not found in the film, not found in the passive film. It is found in the actively corroding areas. So suppose you have a pit, in the deep of the pit you can find molybdenum, or you are going to keep the metal in the active region, and then you observe the surface will have more molybdenum. Okay, but in the passive region, the passive film, there is no molybdenum at all. Okay, and so this led to some kind of understanding that the molybdenum, it says it blocks the active surfaces, One kind of hypothesis theory. There is also other hypothesis which says that the molybdenum, okay, corrosion rate decreases when H plus concentration increases. It is a very uniqueness of molybdenum actually, right? You saw before, when the pH of the environment decreases, what happens to corrosion rate? Increases, right? But molybdenum has a different characteristics. When you increase the acid concentration, the corrosion rate of molybdenum decreases. This is called as a negative reaction order. Okay, suppose you have a molybdenum on the surface, and if you increase the acid concentration, it is not going to corrode. Why? Because molybdenum has a negative reaction order, okay, negative reaction rate order, and so this is considered as the other kind of factors. The other people call it as molybdenum is a getter for chlorides. It can complex with the chlorides. Chlorides are the species which promote corrosion, right? In the pit you have more chlorides, and the molybdenum forms a complex with the chlorides, and then so what happens? The free chlorides are very less, and so pitting is decreased. There are also other theories talk about semiconducting theories. The passive film is considered as a semiconductor, right? It is like high temperature oxidation, right? You have oxide film, it is considered as either rich in oxygen or less in oxygen, non-stoichiometric oxygen there, right? Then you have either p-type or a n-type oxide conductors. So similarly, you can also consider passive film as a semiconductor, and what you do when add molybdenum has, let us say 6 plus, valency state, then what happens? It reduces, what happens? It will reduce the cations, right. When you are going to add a higher valent ions in the oxide, what will happen to cation concentration? Cation concentration decreases to make the electron neutrality, and so what happens? Then what happens? Lowers passive current. And makes it stable. So there are several kind of theories available. I have just given only a few of them, and there are some more theories. I think again, for this course we do not have to worry too much about the mechanism, just an outline of the mechanisms are okay. The nitrogen has a similar role. About nitrogen, still not clear. Some people say it forms ammonia, that means it neutralizes. But what happens is, we have seen that the active dissolution is decreasing, active dissolution. Is reduced due to nitrogen in the alloy. Now we also have the microstructures. Let us go to microstructures. Suppose you have some phases which are selectively corroding, like manganese sulfide, what happens? It lowers pitting resistance. They selectively dissolve, attack actually. So any phase which are prone to corrosion, they will promote the corrosion. Similarly, segregation of elements promote pitting. I give an example. You weld it. If you weld, what happens now? What has happened to the material when you weld it? The weld fusion zone, what happens? Some of you guys are having metallurgy background, right? When you weld it by, let us say, fusion welding, okay, TIG welding or a MIG welding, you take a stainless steel and weld, what will happen? If you look at the microstructure, what do you see the difference between the welded fusion zone and in the base metal? I am talking fusion zone. You take a nicely rolled wrought stainless steel sheet and you weld it, and the fusion zone, what do you get? What structure is that? No? Have you heard of a cast structure and wrought structure? Have you ever heard of? What kind of structure you will have in a casting? Suppose you melt and pour it. What structure do you get in a casting?
Dendritic structure.
Dendritic structures. You see, they are very simple, right? See, normally all your stainless steel, they are all, they are, you have a molten liquid, pour it, and then you do, they do hot rolling and then anneal it out, they make it chemically homogeneous. But when you weld it, you are going to have elements which are segregation. Of course, we do not have time to discuss those issues. Okay, the welds are, you will have chemical segregations. like you may have segregation of chromium, molybdenum and things like that. So, you have some place which is enriched with the chromium, some place it is depleted with the chromium. What will happen to pitting resistance? The pitting resistance will fall because there are some regions are poor in chromium content, moly content. In fact, if you look at some of the literature published, if you see the percentage of molybdenum versus the critical pitting temperature, okay, and you see that normally the critical pitting temperature goes like that. It is the rod and it is welded. What happens? Welded. I will tell you later what is critical pitting temperature. So, the microstructures play a role because microstructure leads to different chemical variations, and so there are issues of rendering these alloys susceptible to corrosion. The other example is let us say I just give small example, aluminum alloys. That is a very nice system to discuss, and how the pitting resistance of the aluminum alloys really change. The aluminum, unlike stainless steel, will have multiple phases to have the strength, right. In aluminum alloys, alloying elements in solid state, that is accepting magnesium and zinc, increase EPIT. So, they are generally good, but then you do not have you do not make aluminum alloys generally with the elements in the solid solution. You always want to have precipitates to increase the strength performance actually, but from scientific point of view, you can add so many elements like molybdenum, tungsten, chromium and host of elements. If you can put them in the solid solution, and you will find that is a very significant improvement in the pitting resistance of these alloys actually. Okay. Let us look at the other one, metallurgy, cold working. Generally cold working and cold work, what happens? Lowers resistance. Why? It introduces dislocations, and so there will be more corrosion. Surface roughness, okay. Smooth surface favors better passivity. Hence, rough surface is prone to pitting. So, you make the surface if you do electro polishing, make it mirror like, you have excellent resistance to pitting at all actually. One of the factors, external factor like it is not related to metallurgy, external factor like velocity of the environment. So, what do you think will happen to pitting corrosion? You have a stagnant condition, you have flow condition, what will happen to pitting corrosion? Pitting resistance will increase, okay. So it will increases. Why does it increase? Because it will destabilize the pit chemistry, right? It destabilizes the pit chemistry. Is destabilized. Hence increases pitting resistance. Okay. So we have seen overall the factors that are controlling the pitting corrosion. Then it must be easy for you to suggest methods to prevent pitting corrosion. How do I avoid pitting corrosion? Quickly, yeah. So you can choose an alloy, choose a right alloy. Or what you can do, you can, yeah, you can change the surface state. To some extent, it is not going to be okay for long run, but yes, it is good. Third, environment change where possible. If you are going to apply a material for seawater application, obviously you have to choose a right alloy, right? You cannot really do much about it, right? But if you are talking about a cooling water system or a boiler water systems, you can change the environment, right? You can lower chlorides, you can do that. Add additives, the temperatures. Then what happen? Velocity. That means avoid stagnancy, right? If you are going to talk about seawater application, one of the very robust alloy system is what? Titanium, right? Titanium forms a very strong passive film, and so it is more resistance to pitting corrosion. You have of course tantalum, okay, the ultimate in terms of corrosion resistance and pitting resistance, okay. Okay, so let us go to the last topic of this, which is testing and evaluation. Okay, there are ASTM standards for that. Okay, you can look at the ASTM standards. In ASTM U48, and this talks about the 8% ferric chloride solution. It determines the critical pitting temperatures. Okay, critical pitting temperature is determined. What you do in this case is that you immerse it for about 72 hours, maintain the temperature plus or minus 2 degree accurate, find out the highest temperature below which no pitting occurs. The highest temperature below which no pitting occurs. That is called critical pitting temperatures. pitting is not found. Second one is also we have ASTM G61. It is cyclic polarization. Okay. What you do here, you determine E pit, you determine the E repassivation potentials essentially, right. See, I am not going to give you all these details, you can read this in the standard, is available in the library, okay. I will tell you what is important here. One is the scan rate. Higher the scan rate, you get higher the pit values, because okay. So you have to maintain the scan rate as stated in the standard 0.6 volt per hour. There are some problems you normally encounter. If you do 0.6 volt per hour, sometimes you will get a crevice attack in the samples. You know, sample sometimes you mount it, no? You have a mount here, you keep the sample, you know, this is a sample, and you may get a crevice attack. You must ensure that there is no crevice attack taking place. If there is a crevice attack, then E pit will be lower than the actual value. Why? Before pit occurs, the attack takes place along the interface here. So mounting the sample properly, ensuring that there no attack occurs at the interface between the sample and the mount is a very important thing. In our lab, we apply a small bead of epoxy resin, and so that the interface is protected from that. There are also special electrochemical cells available. I think we will not discuss here. You can see them in the literature actually. What is more important is that this reversible current, what we talk about here, is 5 milliamperes per centimeter square. Now, if this is not maintained, the reversible, see, for example, if I just scan like that and I just reverse it here, you get like this. If I, on the other hand, if I reduce this current even more, I get like this. So this repassivation potential ERP, whatever you write here, ERP, depends not just on the material, it depends upon at what current density you are reversing the scan, right. I hope you will be able to understand why does it takes place. If you apply more current, the pit becomes deeper, it becomes difficult to repassivate. If the current is lower, the pit is shallow, it is easy to repassivate. So repassivation of the pit does not depend only on the metal, but also depends upon the depth of the pit. So, but what they have found here is, if you are going to apply 5 milliamperes and above, it is not going to depend upon this current. So in fact, it was done, work was done in Southwest Research Institute by Narasi Sridhar and group, where they have shown that if you have a critical pit depth beyond which it is not going to affect the repassivation potential. So that means you need to follow this standard meticulously, without which you may get a different ERP value, which is not an indication of the pitting growth resistance tendency of the metal actually. Please look at this, talks about pitting initiation, and this talks about the pitting repassivation here. Now look at this, this is called a hysteresis now, right. When you do this, I think we discussed earlier in the earlier class, did we discuss this one or not? Did we discuss this one? No. Okay, so then I spent a minute on this to discuss what it is, so that you will understand it better. See, here you can say the pit is initiated, When you advance the potential more and more, what happens? Here new pits initiate, old pits grow, isn't it? So here it becomes a stable pit here, right? So beyond this, what happens? The pit that is formed here is stable, but when you start increasing the current further, which means you are going to increase the potential also. Now what happens? The new pits are going to form, the old pits grow. Now what is happening now when you reverse this current here? Please see this. It is not following the same path. Rather, what happens now? The current, the reverse current is higher than the forward current, right? Why does it happen? It happens because when you have a pit is formed here, this pit is not repassivated. The pit continues to corrode. Even though you are bringing the potential below the pit, the pit continues to grow because the pit is now seeing a higher chloride ions, it is seeing a higher amount of H plus ions, and the film is totally damaged, it is not healing at all. So when you bring down the potential from here to this, so what is happening now? The driving force is decreasing. The over voltage for the metal to dissolve is decreasing here. So now what happens? The dissolution current is decreasing, it keeps decreasing here. At this particular point of time, we can say the pit is stopped. The walls become passive now. Okay, so that's what really happens now. So that is why this is called as a repassivation potential now. Okay. So we look at the two types of testing for pitting. One is ASTM G48, wherein you use ferric chloride and determine the critical pitting temperatures, and also we also use that particular test to quantify the pitting on scales. If you go through this standard, the standard gives you a lot of view graphs to quantify the scales based on the number or based on the depth, based on the radius of that. We also looked at the electrochemical test where we use cyclic polarization to determine the pitting potential and the repassivation potentials. These two are the important criteria in ranking stainless steel or any material against pitting corrosion in a given environment. Please again notice that the E-pit or E-repassivation potential also depends upon the environment, it is not just only depend upon the material. So these two techniques are very widely used. Obviously, you can't use weight loss measurements to determine the pitting because the apparent weight loss is so insignificant, it does not give you any meaningful information about the pitting tendency of any alloys. The other important character of pitting corrosion is it is stochastic. Okay. What is meant by stochastic? It is more probabilistic in nature. So that makes some kind of constraint in extrapolating any of the experimental data. So this aspect we will discuss now. Okay. Now if you expose a stainless steel or aluminum alloy or any of the alloys which are prone to pitting to a given environment for a given time, and then you observe the pits that are formed on the surface. You would look at the size distribution, you look at the numbers, right, the two types of quantification that you can make, right. So, you can look at the number of pits in a given size and see how it varies. You would probably get something like this. The number of pits against the size of the pits. You see a kind of normal distribution, something like this you will see. What does it really indicate? If you count the number of pits on the lower size and the highest size, both sides are very small in number, right. The average size of pits are large in number. Okay. But if you talk about a component failure, right, what does it depend upon? Suppose you have a pipeline and it has suffered pitting and the leak occurs. The first leak that occurs, does it depend upon the number of pits? What does it depend upon? It depends upon the deepest pit. So, in practice this is what is going to count for us, okay. This is what is going to affect life of a component. This looks little more, even more simple, right. Let us look at the size effect of the specimen tested. Does it really play a role? Now, in order to look at it, we take this as a probability concept here, okay. The probability of occurrence of one size of the pit, okay. For example, what is the probability of this pit occurring? What is the probability? Right. We can also look at the probability of this one, right. So, I can determine what are the probabilities of occurrence of a given size of the pit. I can do that, right. If I can expose the samples of various sizes and determine the probability of occurrence of any of these size pits, I assume, let us say this is the size of the pit, let us say is about this, assume that this is the size of the pit, let us say about, let us say D is the size of the pit, let us say 2D is the size of the pit and 3D is the size of the pit, right. I am giving approximately, okay. And if I plot the probability against specimen size, probability of occurrence of the pits, okay. Let us say 0 and you say 1 probability, right. And I, for simplicity, I also rate the size in terms of unit sizes. Let us say the size of the specimen is 1 unit area, the 2 unit area, 3 and 4, like that I can have, right. Unit 1, this is the 2, 3 and maybe you can say 4 or whatever kind of thing, okay, up to let us go up to 3 only. So what do I mean by that? Suppose I take this is 1 centimeter square, this is 2 centimeter square, 3 centimeter square, right. Let me look at the probability of finding the pit of diameter d, let us see. It is very interesting that the probability of finding the pit d, the sample 1, something like that, goes like that. So the size of this pit, the probability of finding that size of the pit increases when the size of the sample increases. Now I can also find out similar thing for the pit size of 2D. So what do you understand from this particular plots?
If the size is increasing, the probability of finding deeper pits is more.
More. So that means the structure is more in reality. If you are going to go for larger structures, the probability of pitting is going to be larger. The smaller structure, the probability of pitting becomes less. So it is a stochastic process. So in a laboratory, suppose you take a very small size of the sample and somebody takes a larger size sample, it is possible that you may get different results, not necessarily you get the same kind of results actually. So this makes the things more complicated. There are several reasons one can attribute to that. Suppose I take a stainless steel, okay. The stainless steel consists of what? Consists of inclusions, right. The probability of finding an inclusion which affects the pitting is more when the size of the pit, when the size of the sample is larger. So this is one aspect of thing, and people have in fact dealt with this, the probabilistic theory of pitting corrosion, has been one of the important topic of research. We will not go more detail into it. The idea is to expose to you the complexities involved in determining the pitting tendency of any samples. So that is why when you do a test, especially corrosion test, you give all information, size of the samples, environment, the duration, temperatures, because there are several factors that affect the corrosion behavior of the metal. So in this case, the size becomes even more important and relevant for us to consider actually. So that is something you should look at it. This one. And one thing I just forgot to mention about the prevention of pitting corrosion. I think if you can go back to this slide, sometime back we discussed actually. Okay, please recall this discussion. I just want to add, right. We said that the pitting corrosion can be prevented by, of course, choosing a right alloy. Of course, that is a very generic way of talking about it. Okay, and it also can, you need to look at the surface state of the material, how polished or the environmental changes, chloride should be reduced, you can add additives, you can lower the temperatures and you avoid stagnancy and all. But of course, the material selection depends upon what? Depends upon a given environment, right. You know the temperature, you know the chlorides, you know the pH conditions, and so you decide what can the alloy that is suitable for that. And for that you also have tests like critical pitting temperatures, EPIT values. Please again notice these are all ranking of the materials. I do not think that these tests are going to give you any kind of life that you can supposedly you can predict. That is simply not possible so far about the pitting corrosion of the metals. Coming back to this, the first aspect, that is the choice of alloy, and when it comes to stainless steels, you know that, right. You know that you want to increase the pitting resistance. The one way to look at is the composition, which is pitting resistance equivalent number. If it goes high, then I think the pitting resistance increases. But the other way of looking at is you choose an alloy which is not passivating. For example, carbon steel is better than stainless steels. For seawater applications, right. That is why ship hull is made up of what? Made up of carbon steels, right, not a stainless steel. But what is the problem with the carbon steels? The uniform corrosion rate is more, right. The uniform corrosion rate is more than that of the stainless steels. But if you have the problem about uniform corrosion, then you go for copper based alloys. What are the alloys that you can think of? You can think of brass, you can think of copper nickel alloys, right. They are all used in seawater applications. They have reasonably good uniform corrosion resistance compared to carbon steels, and they do not pit, and so they are in fact widely used for seawater application. The other way of looking at it is you have a very strong passivating metals and alloys, very strong passivating, that is we saw a PRA number. Similarly, you can look at titanium, zirconium, these all can be used. Titanium is used actually, okay, for seawater application. Strong oxide films are formed at ambient temperatures, slightly elevated temperatures. Titanium can be very well used. So to summarize pitting corrosion, the pitting corrosion occurs predominantly in the passive metals, right. Only the pitting, I put it as passive system. I know there are metals like titanium, stainless steels, and alloys which are titanium. There are passive in a very wide variety of environments, right. But we also know that you can also passivate many metals, right, depending upon the environment. You make it pH slightly favorable, right? Even steel can do, magnesium can undergo passivations, and in such cases they can undergo pitting, okay. So it is the passive system. It also depends upon the environment, specific anions, I specially put it. Of course, cations also can influence, right. Can cations influence pitting corrosion? Yeah.
Cation accumulation.
Of course, that is another part of it. I am talking about the environment. I am not talking about the cations dissolved in the pit and causing the pH change. Okay, I am talking about external addition of cations.
If they are oxidizing agents.
Yeah, oxidizing agents, right? Your ferric ions, cupric ions, mercury chloride, all the highly oxidizing environments can cause pitting. Environment, of course, but then anions are very important. Okay, we talked about the pitting mechanisms. We looked at especially what? Initiation, then we talk about metastable pitting, then we talk about stable pitting, right. The initiation is governed by what? Film breakdown, am I right? Films start breaking down because of the anions present in the environment. Initiation mechanisms still are not well defined, still not 100% clarity is there. I have looked at the metastable pitting, right. The film breakdown takes place, there is a localized damage, micron or submicron levels, and how do you know it is metal undergoes metastable pitting? If you look at the current oscillations, if you are going to apply a potential in the passive region over the sample and you monitor the current, there is no stable current, there is always a fluctuation in the current, right. And as you move the potential towards the pitting potentials, the fluctuation increases. These fluctuations indicate that there is a breakdown of the film, and then there is again healing of the surface by reforming the film. And the criteria of a metastable pitting turning into a stable pitting, right. What is the criteria for this? When does it become stable? Yeah. When does it become a stable pit?
Pit chemistry.
Yeah, it's a pit chemistry, right? It's a pit chemistry. The pit chemistry is special, right? It has got more H plus, it has got more chloride, so it does not allow the metal to repassivate. So that is governed by what? Salt film, diffusion effects. We also had a criteria called as RI criteria we talked about, right. It also depends upon the potential drop. Between what? Between the pit and the pit mouth. Because there is a potential drop, it does not allow the pit, the growing pit, that front does not allow to repassivate, right. They are kept at a very more negative potentials, the dissolution occurs. We talked about the mechanisms. Then we talked about the factors controlling the pitting corrosion, right. This is environment, and electrochemistry, metallurgy, right. We look at the temperatures, look at the pH, we look at the velocity effect, for example. Okay. They have a very great influence on that. Electrochemistry means what? It is the potential, right. If you are going to move the specimen towards pitting potential, it is going to break. Film is going to break, and you are going to have higher damage to the passive films. We also look at the metallurgy in term, mostly we have seen in relation to stainless steels, right, and how the various alloying elements affect the two parameters, pitting potential and the repassivation potentials, right. We saw that various alloying elements, right. Microstructures. They do significantly affect pitting corrosions. When I say microstructures, it could be all kind of things. It can be segregation of various phases, and we talked about cold work. Right. I forgot to summarize, right, and we also defined what is a pit, right, a pitting factor. It's just not that an uneven corrosion can be defined as a pitting, right. The radius of the pit to the depth of the pit is very important. You should have, the radius should be smaller compared to the depth of the pit. Then only pit can be stable. Okay. Then we looked at what? Looked at the control measures. Then we looked at the test methods. Because you can add one more to this, and metallurgy is a surface state. Okay. Any questions in pitting corrosion so far? Okay, if there are no questions, we will close the discussion on this topic of pitting corrosion.